In this session, we are going to see what demand paging is. So demand paging is similar to paging with swapping, where the processes reside in secondary memory and the pages are loaded only on demand but not in advance. If and only if there is a demand for a particular page, it will be loaded into the main memory from the secondary memory, but not in advance. So in the context of demand paging system, the use of the term swapper is technically incorrect. So instead of swapper, we will use the term pager. So pager is concerned with individual pages of a process, but swapper is concerned with entire process into the memory. So since we are moving only the required page which is on demand, we should not use the word swapper in a demand paging. Instead, we should use the word pager. So here is a small diagram to indicate how swapping is done. So this is the main memory and this is the secondary memory. So if the pages are not required, it will be swapped out from the main memory to the secondary memory, and if the pages are required which are not there in the main memory, then they are swapped in from the secondary memory to the primary memory. So what is meant by lazy swapper? So lazy swapper will not swap the entire process into the memory. It will never swap a page into the memory unless that page is required. As I already said, you are not going to swap the entire process. Only the page on demand will be swapped into the main memory from the secondary memory. So that is why the special name demand paging. So here are some aspects of demand paging. In extreme cases, we will start a process with no pages in memory. So in that case, the OS sets instruction pointer to first instruction of process, which is a non-memory resident. So that will end up in a page fault. If the page I want to execute is not there in the main memory, then it will raise a page fault. Once page fault is raised, the required page will be brought in. So after this page is brought into the memory, the process will continue to execute, faulting as necessary until every page that it needs is in memory. So until every page is required, faulting will be raised and then the page will be brought into the memory. This process continues. At that point, it can execute with no more faults. When all the pages required for execution is there in the main memory, then no more page faults. So this scheme is pure demand paging. So initially it started with no pages in the memory. Then every page when it is required is brought from the secondary to the main memory by raising a page fault, and this process continues until all the required pages are brought into the main memory, and this is called as pure demand paging. And we need some extra hardware to support this demand paging. For that we require a page table, we require a secondary memory. So this page table is a special data structure which will have a special bit to indicate whether the page is there inside the memory or not. If the page is inside the memory, then it will be valid. If the page is not there in the memory, then it will be invalid. Similarly, you have a secondary memory which holds all those pages. Those pages might not be there in the main memory, but the pages might be there in the secondary memory. So this secondary memory is usually a high-speed disk, and it is also known as a swap device because from that only we are swapping the required pages into the main memory. So it is called as a swapping device. So here comes the performance of demand paging. So demand paging can significantly affect the performance of a computer system. The memory access time, which is denoted by MA, ranges from 10 to 200 nanoseconds. If there is no page fault at all, then the effective access time is equal to the memory access time. And if at all there is a page fault, we must first read the relevant page from the secondary memory and then access the desired word. So let P be the probability of the page fault and P lies between 0 to 1. We would expect P to be close to 0, meaning few page faults. If it is close to 0, we have few page faults only. We will assume that there are few number of page faults. So the effective access time is calculated using the formula 1 minus P into the memory access time plus P into page fault time. To compute this effective access time, we must know how much time is needed to service a page fault. So a page fault will cause the following sequence of actions to happen. First, it will trap to the operating system. Then it save the user registers and process state. Then it determine that the interrupt was a page fault. Then it checks the page reference was legal and determine the location of the page on the disk. Then it will issue a read from the disk to a free frame in the memory. It will wait in a queue for this device until the read request is serviced. Then it will wait for the device seek. Then it will begin the transfer of the page to a free frame. Coming to sixth step, while waiting, allocate the CPU to some other user because we need some time to bring the required page from the secondary memory to the main memory. So till then the CPU will be idle. So while waiting for that process to happen, we will allocate the CPU to some other user. Then receive an interrupt from the disk input-output subsystem that the I/O is completed. Again, I will save the registers and the process state for other user. Then I will determine the interrupt was from the disk. Previously, the interrupt was a page fault. Now the interrupt was from the disk. I will correct the page table and other tables to show that the page is now in the memory. Then I will wait for the CPU to be allocated to this process again. And then I will restore the user registers, the process state, the new page table, and then resume the interrupted instruction. So these 12 steps will happen in sequence during a page fault. But it is not necessary that all these 12 steps to happen. So when the CPU is allocated to another process while waiting for an I/O, it will allow multi-programming to maintain CPU utilization, but requires additional time to resume the page fault service routine. So in any case, we are faced with three major components of the page fault service time. One, the time to meet the page fault interrupt, the time for reading the required page, and to restart the process. For example, if the average page fault service time is 8 milliseconds and the memory access time is 200 nanoseconds, then the effective access time is calculated by using the formula that we have discussed. P be the probability, as I already told, it will lie between 0 or 1. So from this calculation, we can see that the effective access time is directly proportional to the page fault rate. So this shows the importance of the page fault handling. It is directly proportional to the access time. So what are the advantages of this demand paging? You will have large virtual memory. You will use the memory efficiently, and there is no limit on degree of multiprogramming. Coming to disadvantage, you may have number of tables and the processor overhead for handling this page interrupts are greater. So that will be the disadvantage of demand paging. Hope you are clear with what demand paging is. Thanks for watching.